Welcome back to A320 Knowledge, your trusted source for Airbus expertise. Today, we'll be diving into Airbus's guidance on the high angle of attack protection.
The goal of this video is to demonstrate the role of the high angle of attack protection on Airbus fly-by-wire aircraft. It shows the visible effects for the flight crew on the primary flight display. This video is based on an A320, but the principle of the high angle of attack protection is applicable to all Airbus fly-by-wire. This protection is designed to prevent flight in excessive angle of attack while ensuring optimum performance in extreme maneuvers, for example wind shear or EGPWS warnings. As indicated on this illustration, when the angle of attack increases, the lift coefficient also increases, up to a maximum value that defines the angle of attack for the stall. The role of the high angle of attack protection is to prevent the angle of attack reaching this maximum value. Under normal law, and in manual flight, when the current angle of attack becomes more than a specific value, named alpha prot, the high angle of attack protection activates. Without pilot input, the aircraft will maintain an angle of attack equal to alpha prot. The angle of attack can be increased by pilot input, up to a maximum value equal to alpha max, obtained when the side stick is maintained in the full aft position. As a reminder, on the PFD, the following two speeds are functions of the current aircraft angle of attack. V alpha prot is a prediction of what the aircraft speed is when the aircraft flies at an angle of attack equal to alpha prot. It is the speed indicated at the top of the black and amber strip. V alpha max is a prediction of what the aircraft speed is when the aircraft flies at an angle of attack equal to alpha max. It is the speed indicated at the top of the red strip. Another speed in the low speed domain is the VLS. Its computation does not depend on the angle of attack. During a turn, the lift vector is inclined, and the total lift produced by the wings must be increased to maintain a level flight. This causes an increase of the load factor. At a constant speed, the angle of attack is thus increased, and the V alpha prot rises on the PFD. The increase of the load factor caused by the increase of the angle of attack also occurs when a climb is initiated or when leveling off. Therefore, in these situations, V alpha prot and V alpha max will increase as a result of the increase of the current angle of attack. Let us now check what is displayed for the flight crew on the PFD in these different situations. During a level turn with autopilot engaged, the bank is limited to a predetermined value. This limitation of the bank angle also limits the load factor experienced by the aircraft. Here, the V alpha prot strip moves as the load factor increases. VLS and green dot speeds do not move, as they are not a function of the angle of attack. Therefore, the V alpha prot strip can reach and exceed these speeds. When in manual flight, the bank angle and therefore the load factor can be even more increased during a level turn. Higher bank angle requires an increased angle of attack to maintain a level turn. It will also cause increased movements of the alpha prot strip compared to flight with autopilot engaged. Similar to a turn, when climb is initiated, the load factor will increase due to the temporary increase of the angle of attack. This will cause the V-alpha prot to move upward. In manual flight, any sudden variation to the load factor when the aircraft levels off can also cause a rapid variation of the V-alpha prot strip. As the extension of the speed brakes degrades the lift and modifies the wing aerodynamics, it will generate an increase in the value of both VLS and V-alpha prot. This increase depends on the deflection of the speed brakes. Here, during a deceleration with the use of speed brakes and autopilot, the V-alpha prot and the VLS increase. Depending on the aircraft models and on the computer standard installed for flight controls, the deflection of the speed brakes can be different with autopilot engaged or in manual flight. Here in manual flight, we can notice a rapid increase of the VLS and V-alpha prot due to the full extension of the speed brakes. In this sequence, the aircraft flies level, and the flight crew intentionally reduces the thrust to idle, which disconnects the autothrust. Due to the fact that autopilot maintains the current altitude, speed begins to decrease. On the A320, the high angle of attack protection will activate when autopilot automatically disconnects at alpha prot plus 1 degree. Then the aircraft pitches down to decrease the angle of attack toward alpha prot. Here the flight crew pulls on the side stick that maintains the angle of attack at a value above alpha prot. In addition, we can also notice the activation of another protection, the alpha floor function, that automatically sets toga thrust in order to increase the aircraft energy. When in manual flight, the high angle of attack protection will activate as soon as the angle of attack increases above alpha prot. During a slow deceleration, this means when the V-alpha prot increases above the current airspeed. This situation occurs, for example, during a turn at low altitude with inappropriate thrust management by the flight crew. Here we can also notice the activation of the alpha floor function. This function is triggered before the current speed reaches V-alpha prot due to the rapid deceleration of the aircraft.
Thanks for tuning into this tutorial on the high angle of attack protection.